Hi guys, today we're going to talk about section 7.3 in the notes. Our first objective is we want to be able to calculate the mean and the standard deviation of a sampling distribution of a sample mean. So section 7.2, we talked all about sampling distributions for proportions. This time we're going to talk all about sampling distributions for averages. So if we have a dot plot, okay, each dot represents the average of a sample of a certain number of people that were polled, or items, or whatever it is. So if n equals 25 and we talk about the number of, let's go back to that cousins example, right? So if we go through cousins and you have 0, 2, 4, 6, 8, all right? I guess they really should be at the whole numbers. I apologize, but you get the general idea, okay? So this dot would be a sample of 25 people had an average of 4 cousins, okay? This dot would be a sample of 25 people had an average of 7 cousins. Now, for 25 people to have an average of 7 cousins, that means that there's a lot of cousins that everybody has, okay? Here, this would be that 25 people had an average of 1 cousin, which means that they all pretty much have no cousins, right? Very few. Because for 25 people to have an average of 1, those numbers need to be small. For 25 people to have an average of 7, those numbers need to be larger. Okay, so when we're talking about this, just like when we did proportions for means, all right, then the sample mean of the distribution of all the means is going to be the mean of x bar. The mean of the distribution is equal to the population mean. The standard deviation of the distribution is equal to the standard deviation divided by the square root of n. Just like the proportions problems, these two items are on our formula card as well. They're on the back, right? Notice up here it said sampling distributions for proportions. Here it says sampling distributions for means. So we are working on means, and we're going to have, this is for one population. Right now we're dealing just with one, right? We're going to have the mean of x bar is equal to mu, and the standard deviation of x bar is equal to sigma over root n, which we have right here. So these two guys are on your formula card. So, number 1, suppose that the number of movies viewed in the last year by high school students has an average of 19.3 with a standard deviation of 15.8. So that's for all high school students. Now, if I take a simple random sample of 100 high school students and I want to calculate the mean number of movies viewed by those 100 kids, all right, if we did repeated samples of size 100, what would be the mean of all of those samples? All right, well, the mean of the sampling distribution is equal to the mean, which is 19.3. All right, what would be the standard deviation of the sampling distribution? The standard deviation of all of those repeated samples is going to be equal to sigma over root n. So 15.8 divided by the square root of 100 would give us 1.58 movies. Okay. Now, I also wrote, check that the 10% condition is met. And I actually have that down here. I put this in a little silly order, sorry. But when you have your 10% condition, this is the same exact idea as proportions. Your population has to be at least 10 times your sample size. To use these standard deviation formulas, you have to always check, is your population at least 10 times your sample size? So we would check to make sure, is our population at least 10 times our sample size? Is it 10 times 100? So we've got, is our population of all students, all high school students, is that at least 1,000? Yes, absolutely, that's reasonable to use. Okay, and it's required, again, that you always check this. If you're using this formula, this has to be confirmed in order to use this formula, just like for proportions. Right? The other condition, because you always have to check both of these conditions, so whatever notes you make for yourself, all right? The other one, so last time for proportions, in order to use the normal curve, we had to check n times p is at least 10 and n times q is at least 10. Well, for averages, we can't use that because we don't have P and Q. So instead what we're going to do is we have to check the original distribution. If the population is normal, then you're good to go. Okay, you would just say, since the population is normal, I'm allowed to use the normal approximation. Because if the whole population is normal, then the sampling distribution is also going to be normal. However, if the population distribution is not normal, if you are not told, then what we need to talk about is something called the central limit theorem. And the central limit theorem tells us, and I'll come back up to it up here, that the sampling distribution of X bar will be approximately normal if your sample size is greater than 30. This is a standard cutoff for statistics for pretty much the rest of the year for us. If your sample size is greater than or equal to 30, then no matter what the original population distribution looks like, when you do all the repeated samples, that sampling distribution will be normal. So the original population could be as skewed or as chaotic as can be in their graph. But if the sample size is greater than 30 and you repeat all those samples, that sampling distribution, that will have a normal graph. Okay? Your central limit theorem back here is saying that when you do a simple random sample of size n, okay, and then your central limit theorem, which we abbreviate CLT, says that when n is large, large being greater than 30, the sampling distribution of the mean is close to the normal distribution. As we keep repeating those samples and we graph all those results, it's going to be normal, as long as n is greater than 30, greater than or equal to 30. So, if we talk about some problems, right? The scores of individual students on the ACT Composite College Entrance Exam have a normal distribution with a mean of 18.6 and a standard deviation of 5.9. So question A is actually from chapter 2. All right. What's the probability that a single student randomly chosen from all those taking the test scores 21 or higher? So we just want one kid. So this is where we look at, remember when we did our z-score formulas, because I'm going to show you how this comes together. All right, our z-score formula was z equals x minus mu over sigma. So for this problem, and if we sketch our curve, right, we've got 18.6 in the middle. We want to know the probability that a kid gets a 21 or higher. Okay, if we did the z-score formula, we would do 21 minus 18.6 over 5.9. And that would give us a z-score of 0.41. Okay, and when we do that, remember, a z-score always has a mean of 0 and a standard deviation of 1. So if we were to look at the curve regarding the z-score, the mean would be 0, the z-score would be 0.41, and we would shade to the right. Okay, so if we follow that process and we use our calculator, I don't have the answer written down for some reason. Oops. So I would have my lower bound is 0.41. My upper bound is a big number, mean of 0, standard deviation of 1. And I would get an answer of 0.3409. So my area would be 0.3409. Now, you guys might be saying, well, why can't I just use the numbers from the problem? You can, but we got to be careful now, okay? And I'm going to show you why. For this problem, right, if you wanted to just use the numbers from the problem, we can. We would have norm CDF of 21 to infinity, mean of 18.6, standard deviation of 5.9. Okay, lower bound, upper bound, mean, standard deviation. Back here we had, it was 0.41, I don't have enough room, so 0.41, infinity, 0, and 1. Okay, for our norm CDF. Now, you might be like, well, where does the central limit theorem come in? You brought it up, but you haven't used it yet. Well, let's use it now, okay? Now we want to take a simple random sample of 50 students. Okay, so now our n is 50. what are the mean and the standard deviation of the average score for the 50 students? So your average score for the 50 students is the same as your population average. So their average is still going to be an 18.6. But their standard deviation is going to be the 5.9 divided by the square root of 50. Their standard deviation is going to be 0.8344. Instead of varying by almost 6 points, we're only going to vary by less than a point, 0.83 points. Remember, what do you have to check in order to use that? You have to check, is your population at least 10 times your sample size? Which, yes, absolutely. Okay, our population of all ACT tests, or all ACT takers, is at least 10 times 50. Yes, of course, there are more than 500 kids who take the ACT test. Now, the second question said, do your results depend on the fact that individual scores have normal distribution? No, they're going to be independent, okay? So these results are going to be independent of the shape. Since your population is normal, absolutely everything else is going to be normal. Now, C is saying, what's the probability that the mean score of these 50 students is 21 or higher? Back here, we said, what's the probability that one student got 21 or higher? Now I want the probability that 50 kids average up to be a 21 or higher. So your formula, the picture is actually the same. Okay, you still have a mean of 18.6. We still want higher than 21. But remember when we talked about the z-score idea? So there's like two ways you can approach this problem. One way is to use the z-score, but to use your z-score for these, it's really z equals, it's going to change a bit. It's x bar minus mu over, but our standard deviation is sigma over root n. Okay, it's the standard deviation we just found here, sigma over root n. So when I plug stuff in, it's 21 minus 18.6, but this is 0.8344. So my z-score is actually 2.8763. Back here, one kid, my z-score was 0.41. Now my z-score is 2.876. So it's almost 3 standard deviations above the mean. If you use your norm CDF for this, right, and if you think about the idea of a z-score has a mean of 0, same picture, it's just going to be 2.8 here. So we would have 0 and the 2.876. I can't fit it. Norm CDF of that 2.8763 to infinity, mean of 0, standard deviation of 1, gives us an area of 0.0020, or a 0.2% chance. Now, what I said back here, you got to be careful. If you use just the numbers from the problem and you don't use the z-score approach, and both are acceptable, but you have to be really careful because it's going to start out the same, right? You're going to have 21 infinity. The mean is 18.6, but the standard deviation is not the standard deviation from the problem. It's this. It's 0.8344. If you use the 5.9, then you never actually brought in the root 50, which we need to use. The root 50 makes the standard deviation be 0.8344, and you'll get an answer incredibly similar to this. So for part D, all right, what if we change? What if we say, what's the probability that now we're going to take 75 kids, and what's the probability that all 75 kids are going to have an average that's 21 or higher? That got even more difficult, right? More kids to have a really high average is going to be harder to achieve. So the z-score, if we use that approach, is going to be 21 minus 18.6 over, this time it's 5.9 over root 75. And our z-score is 3.523. So our z-score got even bigger. 1 kid, z-score 0.41. 50 kids, z-score 2.88. 75 kids, z-score 3.52. So when you do norm CDF, you're going to have 3.523 to infinity, mean of 0, standard deviation of 1. You're going to get 0.000213. So this is a 0.02% chance. This was a 0.2% chance. This was a 34% chance. 34% chance for 1 kid. 0.2% chance for 50 kids to have an average that high. A 0.02% chance for 75 kids to have an average that's that high. All right, so if we talk about peanuts now, all right, at the Peanutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of the weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. So, without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar and finding that the contents weigh less than 16 ounces, or randomly selecting 10 jars and finding that the average contents weigh less than 16 ounces. So think about that on your own. All right, and I have that it is more likely that a single jar weighs less than 16 ounces rather than an average jar, an average of 10 jars weighing less than 16 ounces. It's way more likely to find one that's less than that rather than 10 averaging up to be less than that. Okay, now if we go to the next page to find the probability, and you guys try this on your own, find the probability for part B that a randomly selected jar contains less than 16 ounces of peanuts. So we want a jar. So pause the video, try it, unpause, take a look. Okay, you could have solved it 2 different ways. If you chose to solve it with the z-score, I found my z-score, remember it's a jar. So I found my z-score to be negative 0.67, and then I got 0.2514. Or if you use the values from the problem, your normal curve drawing would match that, and you would get 0.2525. Whereas part C is saying find the probability that 10 randomly selected jars have an average less than 10 peanuts. Okay, so I said less than 16 ounces of peanuts on average. So this is where you need to do your other standard deviation. Okay, so I have my z-score here. I did my z-score formula with the new standard deviation, and my z-score jumped from negative 0.67 to negative 0.211. That is way lower than the mean. Okay, remember, your z-score represents how many standard deviations above or below the mean your data is. Don't forget that you have to acknowledge, you have to check your population of all jars of peanuts is going to be greater than 100. Then when I do that and I use my z-score, I got 0.0174. Okay, so 1 jar, 25% chance that it's less than 16 ounces. 10 jars averaging up, there's a 1.7% chance. It's so much smaller. So what I'd like you guys to do is I'd like you to do number 4 on your own. Okay, set it up, see what it's looking for. Be careful. One of the first things, right? Suppose that the number of texts sent during a typical day by students at a particular high school follows a right-skewed distribution with a mean of 45 and a standard deviation of 35. How likely is it that a random sample of 50 students will have sent more than a total of 2,500 texts in the last day? So they're mixing together a couple things, right? So first you're like, wait, it says right skewed. But this is what that central limit theorem is saying, that even if your population is right skewed, if your sample size is greater than 30, which it is, we have 50, then the sampling distribution is going to have a normal shape. Okay, so even though the original is right skewed, we can use the normal distribution in this problem because our sample size is great enough. And you're going to have to just make a note of that. Okay, the other thing is that if we have a total of 2,500 texts in the last day, I went with the approach here that I'm going to let x equal the average number of texts for each student. So if the total is 2,500 and there are 50 kids, then really I'm looking for the probability that each kid is that the average per kid is going to be greater than 50, right? You could have also brought everything up to the totals. I brought everything down to be each kid. All right, so go ahead from here, cruise through, pause the video, check it all, like do it all. Now check against mine. Okay, I had my mean, my new standard deviation. I checked that it's reasonable that the number of students at the high school is at least 500. Large counts condition, since n is equal to 50 is greater than 30, it's okay to use the normal distribution. Okay, back here, we didn't need, in the peanut problem, I didn't need to check that because I was told that the population was normal. So since the population was normal, I didn't need n to be greater than 30. But this time, the population is right skewed. So in order to use the normal distribution for the sampling distribution, I have to make sure my n is greater than 30. And you have to state it. Okay, so then I said, all right, I chose to use the values from the problem this time, okay, with the new standard deviation here. Oops, I'm off the screen, sorry. Here's my new standard deviation, right? So I got lower bound, upper bound, mean, standard deviation. However, you could have done the z-score with this formula, and that would be perfectly fine as well. Alrighty, so, and your z-score would have come up like around 1, I believe. Good job. Here's the homework problems if you want to get started on them. I'll specifically tell you through Google Classroom when we're actually doing them. Nice job today.